All right, so let's get started. This is basically everyone who starts computer vision. It is a hard problem because the amount of learning that you have to do, like, but the amount of learning you come out with just having done as a normal human is amazing. Just like you can tell different characters apart, you can like tell shades of light apart. It's pretty amazing. Teaching a computer how to do that is a very hard problem. Also, one of my professors said that. That's why I put this here. All right, so let's talk about the agenda a little bit. I am a little pressed on time when it comes to this presentation and like this whole workshop. So we're gonna hurry along. If you have any questions, ask me like anytime, interrupt me in the middle. Zoom people, you're gonna have to like rely on Rob or someone else because I don't really check the chat that much. So we're gonna go over some basics. I'm gonna go over like a gentle introduction to neural networks and convolutional neural networks. I'm also incidentally going to talk about the difference between AI, machine learning, and deep learning, because those three things are used pretty much, those three terms are pretty much interchangeably used and they are not the same thing. Then we're gonna do an image classification demo. And then I had planned a Spooktober themed cool demo. Spooktober themed would be something that Redditors would know, but I don't know if it's gonna work now because screen share, camera, Zoom, my computer being really bad. Let's see. And then we'll take questions at the end if needed. Sound good? Okay, cool. Let's start with disclaimer. Here's the thing. Computer vision is a very, very huge field. There is a lot of things, a lot of research going on in this field. It's evolving every second, and there is no way that I can cover even the basics in 40 minutes. I am going to try my best, though, and hopefully that helps. But I am going to link other helpful resources if you guys are interested in pursuing this further. And if my demo does not work, we're going to look at like an external, like something that someone else has like hosted. So with that out of the way, let's get to the basics. All right, so neural networks. First of all, let me just pull up a diagram. I pulled this up and I made this diagram myself because I didn't want to credit anyone. It is my slide. So yeah. Neural networks, I'm sure you guys have heard of the term. These are mathematical functions, basically. Functions as in you put input, you get output. That's a function. These are biologically inspired. They are inspired by your brain. Your brain is amazing at what it does. And according to some like really smart people out there, we're very, very far away from general intelligence, which I agree with. We can have that conversation some other time, though. A neural network is a building block of deep learning. So now let's talk about the difference between AI, machine learning, and deep learning. So AI is, you can consider it basically a superset. Has anyone tried to write like a really like minimax algorithm to solve like a chess puzzle or even like a Sudoku solver? You just programmatically put in all kinds of situations and like what the optimal scenario is. That is artificial intelligence, right? It's artificially intelligent because it's able to differentiate between different situations and like different stimulations and get like different outputs according to what is required. And it's able to do that somewhat intelligently. Machine learning is a subset of artificial intelligence. It includes neural networks and deep learning, but there's also more. So there is this algorithm called K-nearest neighbors, for example. This is not a neural network algorithm, but it is qualified as a machine learning algorithm because it learns from inputs. And then finally, deep learning, which is the revolution that we're in right now. And this includes the neural networks. So let's talk about a neural network. Yeah, all right. So I'm gonna do some pointing here. I don't know how I'm gonna like help the Zoom people. I'm gonna try to keep it as context as you can probably guess from what I'm saying. So let's start all the way at the left. This is the input layer. You're gonna feed images, stimulus. You can probably feed in like all the position of all 32 pieces on a chessboard in here. Depends, like each piece will probably be like one node. Now, terminology. One of these circles is called a node. You can think of it as a neuron, and that's why they're called neural networks. I don't like that term, so I'm just going to call them a node. These nodes do some processing on whatever input they get. They're going to do some sort of mathematical function on it, and then they're going to process that information and feed it forward to the next layer. The middle layers between input layer and output layer are called hidden layers. Now, for the sake of simplicity, I only put one hidden layer in here. Also, we have some stuff in the chat. I am very reliable, don't worry. Oh, okay, cool. Thanks, Rob. Sorry, where was I? Yes. So this middle part is called hidden layers. For the sake of simplicity, also, I didn't want to like draw too much. I only put one hidden layer, and this is a very common representation. So you can think this is an example of what's called a fully connected neural network, and we're going to get to that in just a bit. But what I want to explain to you is that information comes in here to the input layer. Each node does some processing on whatever information it gets, feeds it forward to the next layer. In the middle, these little lines between the two layers, they're also going to do some, there's also going to be, at least if you like think about it abstractly, it's helpful to think of it in a way that these middle lines are doing some processing on it. The hidden layer is going to do some processing on it, pass it forward to the output layer, or like the hidden layers are going to do some processing on the data and then passing it along to the output layer, which is then going to give whatever result it's going to give. So now let's talk about weights and biases. Or I'm going to hurry up a little bit. So remember where I was talking about the lines, the connections between nodes? Those lines are like what I said was the lines are doing some processing on it, right? So let's take a look at this formula. Keep that in your mind for a second, and we're going to go back a little bit. So each of these nodes, this node, they don't do some processing on whatever data they get, and they pass it forward to the next layer. So these little arrows that connect this one to this one, the processing in the middle there, what's happening is that each node in the hidden layer, for example, has connections to all the nodes of the previous layer. So the bottommost node of the hidden layer is connected to both nodes of the previous two layers, right? And it basically assigns a weight to each one of them. So let's say that the topmost node in the input layer is called node A, and the topmost and the bottommost node in the input layer is called node B. So then the hidden layer's bottommost node, this node, let's call it node 3, assigns a weight to this one and a weight to this one. So a weight for A and a weight for B. And then it'll multiply A and B's output, which is its input, and it's going to call those are called weights. And then it's going to take all that sum, and it's going to add that to a bias that it has. So this is the bias of the node itself. And let's talk about like the learning that happens in a machine learning, specifically deep learning. So the learning that happens in deep learning refers to the changes in these weights and biases. By that I mean, let's say that you have, and we're going to go back to the neural network diagram. I love this diagram, by the way. So let's say that we have this diagram, and this diagram is a very sophisticated network that is there for predicting whether a given image is a cat picture or not a cat picture. Sound easy enough, right? So this input layer is going to get images of cats, right? It's gonna do some processing on it, pass it along to the hidden layer. The hidden layer is gonna do processing on it, compress the data, because what we really care about is whether it's a cat or not. We don't really care about the entire picture. We just wanna like essentially like encode the entire picture into whether it's a cat or not. We don't care whether it's a brown cat or if it's a black cat or a white cat. We don't even care if it's like a dog or a brown dog or a black dog or a human being or a t-shirt or a cloth, right? All we care about is whether it's a cat or it's not a cat. So all that information, like think about what the information goes, like think about what information you have coming to your eyes, right? So I'm standing around, I'm moving around. You have this diagram right here, right? All of this information is irrelevant. All you care about is whether the scene you're seeing right now is a cat or not a cat, right? Follow me so far? Okay, cool. So all of that information is essentially dropped in the hidden layer. And machine learning, or at least, and this is an autoencoder, this is trying to figure out what information to drop. You can think of it that way. This is a very cool analogy that I just came up with on the spot. There is a question in the chat. Rob, what is the question? Okay, all right. Sounds good. All right, so now let's talk about how linear algebra comes in here. Now, when I was originally imagining this talk and I was like preparing for it, I thought that I would have a whiteboard and I forgot that I was gonna do it on Zoom. So we're gonna have to be a little bit more creative here. Have you guys seen matrices? How many of you guys have seen matrices? Okay, cool. Anyone in chat who does not know what a matrix is? Oh, I'm assuming there's no one who doesn't know what a matrix is. Okay, cool. So matrices are really cool because a row or a column in a matrix, let's take one column, and if it's a single dimensional column, you can call that a vector. And this hidden layers, each node has a vector, right? It's the vector of weights. So it's the weight that it assigns to node A and node B. Each of these nodes has such a vector, and this is called the vector of nodes or vector of weights. I don't really know if it's called that or not. I just made that term up, but you get the point. So this is where linear algebra comes in, and this is why when you like take courses online to try and learn this stuff, you're gonna come across linear algebra a lot. Like this is where it comes in, and we're gonna get to that in a little bit. So before we get to the action, I want to get some terminology out of the way. And I do apologize, everyone hates terminology. Let's talk about fully connected layers. So we're gonna run back to the diagram, and I'll keep doing that a lot. This is, as I mentioned before, this is what's called the fully connected network. Each hidden layer, each node in the hidden layer has connection to all nodes of the previous layer and all nodes of the next layer. That means like that our favorite node, the bottommost node of the hidden layer, is connected fully to the outer layer, which is its next layer, but it's also fully connected to the previous input layer. What this means in practice, and a lot of times there's a node, for example, that's going to ignore a lot of the information that comes before it, right? It's still connected to it. It's just going to ignore all the information. Therefore, what this really means is that it's going to assign those nodes that it's ignoring the information from a weight of 0, because 0 times anything is 0. Yes, exactly. So that's what a fully connected layer is. There is something else in chat. I am curious now. Gotcha. All right. So the next thing we're going to talk about is activation function. And we're going to run back to the diagram. I should have planned this a little bit better. So You guys remember me mentioning that each node in here does some mathematical processing on whatever input it gets, aside from the weights and biases stuff? Well, it does. So what it does is it's going to take in its input, apply the weights and biases, and then it's going to do some sort of processing on it. And most of the times it applies a nonlinear function on it. Some of the more well-known functions are ReLU, which is rectified linear unit, ReLU, R-E-L-U, SGD, stochastic gradient descent, but that's an optimizer. There's also sigmoid, which is a very famous one. I'm not going to bore you guys with the mathematical formula for it, but basically what it's trying to do is it's trying to come up with new and interesting ways that you can compress the information. And really, all you can, like, neural networks and the whole field of deep learning is just built on matrices and linear algebra. So we're gonna like kind of skip that a little bit there. The thing is, what I want this demo and lecture to be is a practical introduction. I don't want to get too bogged down into the mathematics, but I want you to be aware that there is math behind it. So I don't want someone complaining to me that Arjun didn't go over the math stuff, because I'm all about the math. Let's talk about an autoencoder. And what you saw before, the diagram, that was an autoencoder. And this is like one of the more fancy terms. So basically what an autoencoder does is it takes in some sort of input and it tries to compress that information into some sort of unit, like some form of, it just tries to compress the data by itself and answer the question itself. So for example, we're gonna spoil this a little bit, but no, not fully. I'm not gonna use MNIST, but if you guys have heard of the MNIST one, it's there's 10 digits, handwritten digits. So usually at the output layer, you're gonna have 10 nodes, and whichever node activates the most, which is whichever node has the highest probability, is going to be what the computer predicts that handwritten digit to be. So for example, you're gonna take in a picture, in MNIST, for example, it's a 28 by 28 pixel image of grayscale pixels. Rob, what is 28 by 28? Please do. I should be able to do this in my head. Okay, so 784 pixels of information is there in a handwritten, in an MNIST image, right? And you're gonna basically compress all that information, all those 784 pixels of information, into 10 kind of units, and 10 a vector of 10 probabilities. And whichever is the highest probability is going to be the number that the computer is guessing. So for example, if you put in an image of, feed in an image of 1, right? Then the highest probability that it's gonna give, the computer is gonna give out of the 10 digits is going to be 0.99, for example, for 1. It's gonna give for 0, the probability might be like 0.005. For 9, it might be 0.0001, something like that, depending on how well or how badly you've trained your model. All right, so, oh my God, I'm like not doing very well on time. Backpropagation. Backpropagation is how the computer learns. It's how the neural network learns. There's some calculus behind it. Have you guys heard of chain rule? Okay, do you want me to get into it? Okay. Yes. Max pooling is a kind of it's a kind of layer. It basically just takes your image and compresses it. So it takes the information in like, for example, the 784 pixel handwritten digit, and then just like, depends on how you set the dimensions, but the most common one is to half it, or like to make it a quarter of what it was. So this way, you have less information to deal with. Gradient is a derivative. gradient really refers to what direction your data is moving in. So have you guys heard of derivatives, calculus stuff? Right. So if you take a function, for example, and you take the gradient or derivative of it at a certain point, it's telling you what direction the data is moving in for at that point. And that's pretty useful in computer vision applications for reasons I really can't get to in this because of time. Finally, the multi-layer perceptron. This is a multi-layer perceptron. Okay, so let's talk about convolutional neural nets, and then we'll look at the demo. Oh God, I have 15 minutes. So first, let's talk about image filters, and I'm going to like step out of this presentation, and I'm going to show you something. Let's hope this works. I really should have labeled these things. Give me a second, sorry. Okay, I guess we'll just skip it for now. I'll come back to it in a little bit. Shoot, I really wanted to show that. I don't know why it's not working. So I want to show you image filters, and I had this entire thing prepared, but I guess it's gonna have. Okay, so I had a new notebook prepared with this thing on it, but the thing stopped working on me in the last minute. So yeah, technology is great until it stops working. So I want to talk about image filters first. Image filters, let's take a look at this image. It's an image of stairs, very exciting. You can make it even more exciting by passing it through image filters. So this is something I passed through the image filter. And right away, what do we notice here? Any guesses? Anyone want to throw it out? Yes, it's way more contrasted. And one thing you'll notice here that it's these vertical lines are far more emphasized, right? Like you can see the rails. There's horizontal stuff, right? But that's not emphasized at all. But the vertical lines are all emphasized. And this is an image filter that I've passed this image through during using the convolution operation, and it emphasized certain features of this image. What I'll do is, in the slide there is a YouTube channel that I've linked, which I really like, but also I can have Avery or someone send a couple of YouTube videos demonstrating this concept in more detail if needed. Okay, looking at this one, what do we notice? This is a different filter from the previous one. This one emphasizes horizontal matches far more than vertical ones. So you'll see, for example, that where here, this was far less emphasized, and like this one, so the horizontal part, the part where you grip on the railing, was not emphasized at all. In this image, it is. In this through this filter, it is emphasized, right? Does that make sense? You guys following? Anyone question in the Zoom chat? Feel free to shout out any questions at any time. I'm all about the active learning. All right, so I'm going to stream the presentation again. Yes, I'm going to get to that. Good question, though. People in Zoom, can you see the presentation again? Okay, cool. So we looked at the image filters and we did this practical demonstration. So these image filters in a convolutional neural network, basically you have a bunch of these image filters, like a lot of these image filters that are going to get different, they're going to extract different information from each image. So like, for example, imagine if you had 32 different image filters, for example, and you run the MNIST for like the digit or Keras digit 1, right? So some filters will be effective on it, right? Like the vertical filter that we looked at will be very effective on 1 because, you know, like it really emphasizes that vertical line. Some others will not be effective on it, like the horizontal filter will not be effective. But when you combine all these images over like these filters and run it over a network, and we'll get to kernel sizes in like just a second. What happens is that you're able to extract far more information and like in a far more contrasted way, right? So if we looked at that staircase image, there were a lot of grays. There was very rarely any white or black, right? They were all shades of gray. It's easy for us to be able to tell, but it's harder for a computer to be able to tell the difference between this gray and that gray of shade. So this way, it's able to extract that information far more efficiently. Any questions on that? No? Okay, all good. All right, so this is the end of the presentation. Now I'm going to get to a more practical part. We are going to make a new notebook. We're going to start coding things from scratch. I'm going to give everyone who wants to follow along like a little bit of time if you want to. Zoom people, any questions? Okay, there's something in chat. This is Google Colab if anyone wants to try following. Yeah, I'm actually not doing it in Google Colab. Now that I think about it, that was a bad idea. What I really wanted to do was I wanted to do it on my computer's own runtime. It's like a little bit faster and I'm able to like manipulate the command line. That was really more for the second part of the demo. That's not really working right now. So yay, but let's see. All right, so we're gonna start. First of all, I'm going to rename this this notebook, and I'm running Jupyter Lab. If anyone is curious, I'm gonna assume everyone's with me. You can just pull up Google Colab. You can go to collab.research.google.com, or you can just type Google Colab in Google and get you there. I'm gonna call this. We're doing a data set called Fashion and Mist. So I'm gonna call it Fashion. And let's first get to know the fashion and this data set. And I had everything pulled up again, but because that demo didn't work and I had to restart, everything kind of got lost and then we just got started. So we're gonna play it by the ear a little bit. So we're gonna look at TensorFlow's Fashion and Mist, and there's this nice visualization here. Fashion MNIST dataset is like the MNIST dataset, but it's a bit harder. So instead of handwritten digits, which are kind of sparse, like if you think about like how much space a 0 or a 1 occupies in a whole frame, it's not a lot, right? But if you think about whenever this loads, yeah, if you think about like this bag or like this bag, or for example, let's see if we can find a shoe. All right, so trouser. I need to hurry up. Okay, well, I'll show you in the notebook. But anyways, oh, there we go. So think about how much more space this occupies than like a 1, right? Like not that much more, but this is just trousers. If you go down to like a shoe, and it's like a super zoomed in version of a shoe, then it occupies more space, there's more data, and it's far more complex. For example, look at this hideous nightmare of a trouser. It's got all these shades. I don't know who would want to wear this, but it is technically a trouser. So think about the differences between, for example, and you guys can follow my mouse so people on Zoom can also tell. Think about like the difference between the shade on the black outside here and then this, like this black strap in the middle. It's kind of hard to classify, right? So we're gonna try to do our best in this notebook. It's a bit of a harder problem, but it shouldn't be that bad. So let's talk about the data set. The data set contains, okay, this is wrong. Well, I have a whole list here written down. It contains a t-shirt slash top, trousers, pullovers, dress, coat, sandal, shirt, sneaker, bag, and ankle boot. So there's a lot of things here that you're going to kind of have to differentiate. It's going to be good fun. So whenever my thing allows me to, yeah, okay, there we go. So I'm going to start with importing, oh, this is in Python, by the way. Everyone understand Python here, right? I'm going to assume that's a yes. So yeah, I mean, Python is really the easiest place to get started when it comes to machine learning and computer vision. You can also do C++. If people already know C++ here, then that's something I'd recommend checking out because C++ is, in a sense, a little bit more powerful than Python in terms of not a little bit, a lot more powerful. But Python is convenient because you have, it's easy to get started with. So I'm importing some modules here, some libraries here. TensorFlow is a very popular machine learning library that you can use. It's actually maintained by Google, right? I think it is. NumPy is for manipulating matrices and other things. Like it's used for number stuff. We're going to import matplotlib for our convenience. I'm going to compress those names a little bit so it's easier for us to see. I'm also going to include some neural network specific models for, oh, there's a time there. That's convenient. I wish I'd seen that before. Keep glancing at my watch. Huh? Really? Okay. Well, anyways, moving on. We're going to import some modules from Keras. So I'm going to import so this is usually not how you get your data set. And one of the reasons I picked this data set is because one, it's easier for beginners to get started. And two, I really don't have a lot of time to get into data cleaning and all of those messes that come along with it. I'm importing that data set through Keras. Keras is also maintained by Google, I think, and it becomes part of TensorFlow. All right, so I've executed this cell whenever it confirms that it's finished run. You're not really, okay. Leave it to me and typos. Anyways, so now I've run this cell. Everything in this cell looks like it's fine in terms of importing everything. I am going to import specific stuff for like the model itself, but we'll do that in a little bit. Let's get to know our data set just a little bit first. So load data, and this is one of the other reasons why I picked this set, is really, really convenient. Oh man, I really need to hurry. And you can, all right, I'm gonna get it. I'm gonna explain it, one sec. All right, we're gonna look at some class names. So there was t-shirt. I think there was trouser, pullover. While I'm typing this out, can you guys tell me what your opinion on live coding is? Because I could have done this a lot faster if I had it. Like, I mean, I do have it, but like, if I, yeah, but I think I'll live code it here. It's fine. It's just that if I do a demo in the future, I'll plan accordingly if people don't mind that. Oh, Avery, I'll send you the GitHub link in a little bit so you can share it with people as well. All right, so this is our set. You can see that we have t-shirt, trouser, pullover, dress, coat, sandal, shirt, sneaker, bag, ankle boot. All right, so let's move on. And I have all my notes here. So let's kind of get to know our data set here a little bit. So let me talk about load data here. Load data is a function that allows us, okay, that's before that. Fashionamnist has 70,000 images total of these 10 different kinds of things. And that's really good because the more data we have when it comes to computer vision, the better. So the way we usually do this is that we want to train our model, like we want to first define the model. And let's talk about the life cycle of a model just a little bit. I have notes here on that. So first you want to define the model. I've split it up into 5 steps. I'm actually quite proud of this. So you want to define the model first. Then you want to compile a model. Now compiling a model is really just an efficiency step. If someone's taking notes, then this is something you'd want to note down. Compiling the model is an efficiency step because each of your computer is different. Like it has different model of CPU and GPUs. Some are older architectures, some are newer architectures. So what's cool about these different data sets of different libraries like Keras are that they allow your model, once it's compiled, they allow your model to be, it converts your model into a highly efficient series of matrix transforms intended to be run on your CPU or GPU. Really cool. Then once you've compiled your model, you wanna kind of fit your model. So you're fitting your model. What you're doing is you wanna fit it on whatever training data you have, and this is where splitting your data into. Oh my God, I'm an idiot. I'm a bit nervous. Sorry. This is where splitting your data into training sets and testing sets really comes in, because you don't want to be testing your neural network or model on the same data set that you're training it on, because it's obviously going to do better, right? Like for example, if you think about it, if you're asked, like if you're a baby and you don't know what a cat is, right? And you see a bunch of different cats and you're like, okay, this is a cat, this is not a cat. And then like you come across this like really weird kind of looking species of cat, and you're asked to like test whether it's a cat or not. This really tests your understanding of whether you really understand to differentiate between cats or not. I'm just going to continue going on with my contrived example here a little bit. So that's why you want to split it into training and testing data sets, or training and testing sets, because you train on the train set, and this is where the bulk of your kind of data set goes into. And then after that, you want to test it to make sure that the model, like to evaluate what the real world performance of your model is, right? Make sense? Can I move on from there? Okay, so once you fit your network, now you want to evaluate it, which is really just making sure that it does reasonably well on the testing set. And once you've done that, you can like predict with it. So, right, so like, why are you making a model in the first place? If you already have all the data in the world about all the cats, and you already have it all labeled, then why would you even need to do it? You already have it labeled, right? So then you can use it once you're reasonably confident in your testing predictions. Like let's say it has a 99% accuracy. So then you'll say, okay, fine, I feel confident enough to let it make predictions about the real world now. And then you feed it like, real world cat pictures and say, is this a cat or is this not a cat, right? So that's when you kind of take the training wheels and you let your cat identifying baby go identify cats. I'm just going to pretend I didn't go with that entire example. All right, so let's get to the one thing I'm going to do is normalize the data set first. So normalization is a really good thing because it allows you to, it's just a more efficient way of like allowing your model to work. So we're just gonna divide it by 255 because these images have values. Each pixel here can be between 0 and 255. So that is, each pixel is 8 bits. And for those people who understand binary stuff, good for you. So I'm just gonna do this one thing, and then we're gonna get to know our data set a little bit. Okay. What is wrong here? Okay, cool. So now we're gonna get to know our data set. I'm gonna plot it out a little bit so you guys can see it. And I have like this nice line of code that I kind of wrote down in my notes, so I don't have to fumble around with matplotlib and its weird documentation. You can tell I really prepared for this. How much time do I have? Oh no. All right, we'll keep pretend like there is. Well, I basically knew this was gonna happen. All right, you know what? We're gonna let's look at like this. Okay. Yeah. Give me a second. Yeah. I really want to get to the like model definition. Okay. All right. So this is a shoe, for example. At least I think it's a shoe. I'm not sure what's what anymore. I had like this nice thing that I wanted to do. Anyways, let's go move on to the model definition. And I'm gonna like really try to hurry here. So I'm gonna define the model here. I'm gonna give it the input shape. Okay, don't come here, please. You're making me nervous. Okay. I'm gonna interrupt though. Sorry, like I'm trying to hurry up. What did I set the model as? Okay. All right, so here I'm telling the model what activation function it's going to use. And it's going to be, in this case, it's ReLU. Actually, for faster training, let's just make it a little bit smaller. So I'm just telling it how many nodes it should have. So I'm just telling it now it should have 256. It's going to be a little bit worse in terms of accuracy, but at this point, I just want to get it to like work and like exit gracefully before, you know, eating into their time. Man, I really should have asked for more time. Hold on. You know what? I'm an idiot. Hold on. All right, I think that should work. Okay, cool. It didn't yell at me. All right, so now what I'm going to do is I'm going to compile the model. This is an optimization step, but it's a really good optimization step. So you can look up the specific syntax, but I'm just going to like pretend like I'm just kind of like blitzing through here. I'm going to give it whatever, what losses did I give? All right, so I wanted to get into this, but I don't have time. But this is a sparse categorical data split that we're doing, right? Like we're splitting it into 10 possible variables. and 1 through 10, 0 through 10, they're all 0 through 9, they're all categorical variables. So we're going to use something called a sparse cross-categorical cross-entropy loss function. It's a big word, but it's not really that hard. If you want, I can you can ask the question about this later. Yeah. I'm just going to skip the compilation step. I don't have time for this. And we're just going to finally do a model.fit. We're going to fit the model with the train X and train. I can't type. I'm a bit nervous. Sorry. We're going to do it over 10 epochs. Actually, by this point, I'm guessing well, let's just do 5 epochs because I haven't even compiled the model. Shoot. Oh, my bad. Whoops. Hold on. What did I do now? I didn't run this. I'm such a genius, guys. And it's epochs, not epoch. Yeah, it's just telling me that I should compile the model. I can just show you here. Here, this is a compiled model. I can explain more about this later, and I fit the model here, and then I test its accuracy. This is what it gets. All right, so now one last thing before I go, and I wanted to get to this. This is called. This is a cool demonstration of what you can do with computer vision. Sorry, I didn't do it with this account. I'm just gonna run this notebook. Oh, all right, never mind. I'm gonna have to upload files. But anyways, we're trying to construct face meshes over these faces and then go do cool things with it. So this is an example of a constructed face mesh. Yeah, I thought that this would be cool to do because you can mess around with it. So this basically splits the face into 484 or something different polygons. Let's try to take a quick picture and upload it here. Let's see, do I have camera here? Photo booth. All right, I'm gonna take this picture. Okay, there we go. I'm gonna see if I can find it somewhere. Where is it? Take my very beautiful face and we're just there it is. Oh, whoops! I already had a face mesh on it. All right, well, you can see how this looks on my face. I wanted to do this live, but it just stopped working for me. So I guess that's it for me.